Hi everyone. In this class, we are going to discuss about force between differential current elements. Force between differential current elements. In electrostatic, we have studied that a point charge exerts a force on another point charge. In electrostatic, we have studied a point charge exerts a force on another point charge separated by a distance r. If these two charges are of same type, then they repel each other. Both the charges are the same type, then they repel each other. But when both the charges are of different type, then they attract each other. When both the charges are the same time, the force between two positive charges or two negative charges repels to each other. One charge is positive and another charge is negative. The force between these two charges attract to each other in case of electrostatic. Similarly, in magnetostatic, let us consider two straight conductors. The two straight conductor carries the direct currents I1 amperes and I2 amperes. The force between two parallel current carrying conductors depends upon the direction of the currents. The force between two parallel straight conductors depends on the direction of the current. If the currents are moving in the same direction, both the currents are moving in the same direction, the force. So now consider that two current carrying conductors are placed parallel to each other. Each of these conductors produces its own flux around it. These forces between such parallel current carrying conductors depends on the direction of the current. If the direction of both the currents are same, then the conductors experience a force of attraction which is shown in figure. If the direction of two currents are opposite to each other, then the conductors experience a force of repulsion as shown in figure. So now let us consider two differential current element. IDL is the differential current element. I1 dl1 bar is the first differential current element and I2 dl2 bar is the second differential current element. So let us consider two differential current elements I1 dl1 bar and I2 dl2 bar shown in figure. So note that the direction of currents I1 and I2 are same. Both the current elements produce their own magnetic fields. As the currents are flowing in the same direction through the elements, the force derivative of dF1 bar is the second derivative exerted on the element I1 dl bar due to the magnetic field intensity or magnetic flux density dB2 bar produced by other element I2 dl2 bar is the force of attraction. So that is derivative of dF1 bar is equal I1 dl1 bar cross dB2 bar. So according to Biot-Savart, the magnetic field produced by current element I2 dl2 bar is given by, for the free space, dB2 bar is equal mu naught into dH2 bar. So that is equal mu naught into I2 dl2 bar cross AR21 bar by 4 pi R21 square. Substituting this dB2 bar value into equation 1, we get derivative of dF1 bar is equal mu naught into I1 dl1 bar cross I2 dl2 bar cross A R21 bar by 4 pi R21 square. So the above equation represents force between two current elements. It is very much similar to Coulomb's law. By integrating the above equation, we get the total force F1 bar is equal mu naught I1 I2 by 4 pi closed line integral of L1 close the line integral of L2 dL1 bar cross dL2 bar cross AR21 bar by R2 1 square. So similarly, the total force F2 bar on the second current element due to the first current element is F2 bar is equal mu naught I1 I2 by 4 pi close the line integral of L2 close the line integral of L1 dL2 bar cross dL1 bar cross AR12 bar by R12 square. The next one is force between two parallel conductors. So now we consider there are two parallel conductors. The two parallel conductors are separated by d meters, and P conductor carries the current I1 and Q conductor carries the direct current I2. Both the currents are flowing in same direction. The force between these two conductors are attract to each other. In this figure, in this waveform, both the currents are moving in opposite direction. The force between those two conductors are repulsed to each other. Those two conductors are separated by very small distance d. Therefore, the magnitude of the force is F is equal VIL sin theta. In vector form, F bar is equal L into I bar cross P bar. Consider I as a vector, the direction of the force is perpendicular to the I and B. The differential force is dF bar is equal dL into I bar cross B bar, hence theta is equal to 90 degrees, sin 90 is 1. Therefore, dF is equal dL into IB, or d capital L into IB, or d small l into IB. So dl is the elementary length. The above equation is the magnitude of the force. The force exerted on element, first current element, I1 dl1 bar due to the magnetic field dB2 produced by second current element I2 dl2 bar is dF1 is equal dl1 into I1 into B2, where B2 is mu naught I2 by 2 pi d Weber per meter square, and substitute B2 is where B2 is the magnetic flux density. Magnetic flux density at conductor P due to conductor Q. B2 is equal mu naught I2 by 2 pi d. And substitute this B2 value into this equation, dF1 is equal dL1 into I1. B2 is mu naught I2 by 2 pi d. So that is equal mu naught into I1 I2 by 2 pi d into dL1. So therefore, the total force F1 is equal mu naught I1 I2 by 2 pi d into L. So similarly, the force on second conductor excited by current I1 is F2 is equal mu naught I1 I2 by 2 pi d into L. Next one is Ampere's force law. According to Ampere's force law, the force F bar between two parallel wires carrying currents I1 and I2 is directly proportional to the individual currents I1 and I2, and inversely proportional to the square of the distance between them. Statement of the Ampere's force law: the force F bar between two parallel wires carrying currents I1 and I2 is directly proportional to the individual currents and inversely proportional to the square of the distance between them. So that is F is directly proportional to I1 I2 by R square. So that is equal K into I1 I2 by R square, where K is the proportionality constant. The proportionality constant K is equal mu by 4 pi. Substitute K value into above equation. F is equal mu I1 I2 by 4 pi r square, where r is the distance between two wires, mu is the absolute permeability of the medium, mu naught is the permeability of the free space, and mu suffix r is the relative permeability of the medium. So this is the Ampere's force law.